Here are two more examples of graphical representations of relations. We have the relation given by the equation y squared equals x minus 2. The graph looks like this. We can clearly see that it is not going to be a function because a vertical line will intersect it twice. So, not a function. And the domain and the range, well, looking at it, we see in the left and right direction, it begins at 2 and continues to the right forever. So the domain is the interval from 2 to infinity. And the range, arrows signify that it will be going up forever as well as down forever. So all real numbers. The other one actually is only the bottom half of this graph, given by y equals negative square root of x minus 2. And since we've taken the bottom half, we will no longer strike the graph more than once with a vertical line. Therefore, this is a function. And the domain, since we haven't changed the left or right, is going to be the same. The range, however, will be a little different. We've cut off the top half, so now we're still going down forever. We extend to negative infinity. But up, we can only go up as far as the y value 0. And notice, it's a common error. People will recognize that this is the point 2, 0, and they will accidentally put a 2 here because they're looking at the x value rather than the y value. It's important when you're determining the domain and the range to recognize which are your x values, use those for the domain, and which are your y values, use those for the range. So this should be negative infinity up to 0. What if we didn't have the graph? What if we only had the equation for the last example? Is there a way to tell just from the equation that the domain is the interval from 2 to infinity? In fact, there is, because we have this square root. And if you've ever tried to take the square root of a negative number, go ahead and try it on a calculator. Take the square root of any negative number, negative 5, negative 1, whatever. Calculator is going to give you an error because you can't have the square root of a negative number. If you square any number, for example, if I take negative 3 and try to square it, then that becomes a positive number. And so we can't take the square root of a negative number and get a real number out of it. So whenever we see a square root occurring in an equation for a function or a relation, then we know whatever we're taking the square root of has to be greater than or equal to 0. It has to be non-negative. And so by simply writing that out, writing out the expression that's under the square root symbol, and we set that greater than or equal to 0, this is going to give us an inequality that will tell us the domain of our function. See, if we solve this, we get x is greater than or equal to 2, and lo and behold, that in interval notation looks like this. Okay? So to see another example, if we have the function given by y equals the square root of 3x plus 12, and we want to find the domain, again, whatever expression we're taking the square root of has to be non-negative. So 3x plus 12 must be greater than or equal to 0. And again, we solve. We have 3x is greater than or equal to negative 12. And we divide by 3 on each side. X is greater than or equal to negative 4. And so the domain is the interval from negative 4 to infinity. And you can apply this technique anytime you see a relation defined using a square root in the equation. There's one more situation in which we cannot get an answer. We cannot take the square root of a negative number, but also we cannot divide by 0. Or in other words, we cannot have 0 in the denominator of a fraction. So if we have a relation like this, y equals 1 over x minus 3, this denominator cannot be equal to 0. Otherwise, the expression is undefined. And so, again, we simply state that. X minus 3 is not equal to 0. And then we can solve this just as though this were an equal sign rather than a not equal sign. And we get x is not equal to 3. That's our domain. It's everything, every possible value, except for the number 3. To write that in interval notation would be everything to the left of 3 together with everything to the right of 3. And again, we can use this technique anytime we have a variable occurring in a denominator of a fraction. So if we have y equals 3 over 2x plus 1, then again, this denominator cannot be equal to 0, so we write 2x plus 1 is not equal to 0. And solving this will give us our domain. 2x is not equal to negative 1. X is not equal to negative 1/2. So the domain consists of everything to the left of negative 1/2 and everything to the right of negative 1/2. Notice in both of these examples that we have parentheses because we want to state that whatever our missing point is, negative 1/2 or 3, that it is not part of the domain, and the parentheses tell us that.